Inside the massive star-forming region NGC 6357, intense radiation carves through dark dust lanes and chaotic clouds of gas. Embedded within this turbulent environment is a young star named XUE-10. It is surrounded by a protoplanetary disk, a rotating reservoir of gas, ice, and microscopic solids. If we examine the inner region of this disk, where rocky worlds take shape, astronomical models predict a specific chemical signature. We expect to find a nursery dominated by water. This model assumes that icy pebbles migrate from the colder outer edges of the disk. As they move into the warmer zones closer to the star, their ice sublimates, releasing a dense water vapor into the inner disk. That vapor provides the chemical baseline for the assembly of Earth-like planets, making water a universally expected ingredient in these systems. However, when the James Webb Space Telescope observed XUE-10, the data revealed an environment that is chemically upside down. This chart shows molecular signatures 1.15 astronomical units from the star. The expected water signal is flat, while data shows a massive spike for carbon dioxide. This gas emits from a 300 to 370 Kelvin zone, the precise region where rocky planets grow. This is a highly detailed, undeniable measurement, supported by a greater than 5 sigma detection of 4 distinct isotopic versions of carbon dioxide. Most of our understanding of planet formation comes from calmer, nearby disks that consistently show water vapor in these inner orbits. Finding carbon dioxide where we expect water challenges our standard model of planetary beginnings. It suggests that the molecules available to growing rocky worlds are dictated by the environment, rather than a universal chemical path. To uncover what happened to the water, astronomers used the mid-infrared instrument on the James Webb Telescope, known as MIRI. MIRI does not capture traditional photographs. Instead, it reads mid to long wavelength infrared radiation. Molecules in warm disk gas vibrate and rotate, absorbing and emitting light in specific patterns. MIRI reads these as unique chemical fingerprints. These fingerprints allow scientists to observe how external radiation interacts with the raw materials in a disk, often rewriting the chemical recipe for future planets. XUE-10b is being blasted by far ultraviolet radiation, roughly 1,000 times stronger than the levels found in our local solar neighborhood. This radiation triggers photodissociation. A high-energy ultraviolet photon strikes a water molecule, shattering its atomic bonds, leaving behind fragments of hydrogen and hydroxyl. Beyond this chemical destruction, the radiation may also be physically blocking the inward delivery of new ice. Intense radiation truncates the outer disk, shearing away distant edges and destroying the cold reservoir that normally feeds the inner system. Without incoming icy pebbles to replenish water, localized carbon dioxide gas proliferates and dominates the inner region. While the water signal is weak, this does not mean oxygen atoms are absent. They are simply bound within different molecules. A protoplanetary disk is an active factory where molecules are constantly broken, remade, frozen, and transported by the local environment. The harsh radiation field of NGC 6357 has rewritten the molecular supply chain, altering the chemical inventory available for building planets. Eventually, the gas and dust at 1.15 astronomical units will clump together into solid rocky bodies. A planet inherits a specific history of radiation and transport that shapes its chemical starting point long before it reaches its final mass. If the inner disk is rich in carbon dioxide and poor in water vapor, the growing planets interact with a different set of volatiles, which may influence their early surface chemistry and volatile inventories. Scientists can trace this history through isotopologues. The distinct variations of carbon dioxide in XUE-10 record a specific physical history of the star's birth environment. We see similar fingerprints in our own solar system. Meteorites preserve isotopic memories, proving that our sun also formed in a high radiation environment. These findings do not detect a dry planet. Rather, they provide a template for a different kind of planetary beginning. It appears that planetary diversity begins long before planets exist, driven by the conditions of their stellar neighborhood. There is currently an observational bottleneck. The James Webb Telescope captured a clear spectrum of the inner disk, but it cannot see the entire causal chain. To confirm if truncation and transport disruption are truly to blame, astronomers must be able to observe the cold outer disk. Future upgrades to the ALMA radio telescope array will offer the ability to image these distant reservoirs of cold gas and dust. Facilities like the Extremely Large Telescope will eventually provide the resolution needed to map the fine structure of these irradiated systems. These upcoming tests will determine if radiation, transport, or dust composition is the primary driver of the chemistry in XUE-10. The James Webb Telescope has successfully proven what bizarre chemistry exists before planets are born. To understand why it happens, we must wait for the next generation of tools.